So good afternoon, everyone. Thank you very much for being here to this EPIC online technology meeting on photonics for sea exploration and oceanography. So I'm Jeremy Picot-Clemente, and I'm really pleased to moderate this session. I'm a technology expert at EPIC, and you can find my email address here if you need to contact me. I would like first to give you a few words about EPIC and what is EPIC. EPIC is the European Photonics Industry Consortium. EPIC is the largest industrial network in the world in the field of photonics. Today, we have more than 800 members, 800 companies among the EPIC network, and we cover all the value chain of the photonics industry, from the component manufacturer, to the design and prototyping company, to the end users and the system integrators. We also cover all photonics application, which is wide, from space and defense to biomedical and quantum, but we include also AR, VR, agriculture, photonic integrated circuits, and laser technologies, for example. So photonics is really wide, and EPIC is covering all the photonics industry. And our aim is mainly to create a sustainable European photonics industry. How we do this? So being an EPIC member gives you access to a large panel of services, from technology support to market and technology reports, access, networking events and opportunities, access to markets, mentorship, HR support, and investments. So EPIC is actually a team of 12 people passionate by photonics. So two different teams. Here is the team dedicated to marketing and event management. And I'm personally part of the technology team. So I'm in charge of optics and optical system, and I have also two colleagues, Antonio Castillo, who is in charge of biomedical and lasers, and Ivan Nikitsky, who is in charge of quantum and integrated photonics. Few words also about the next EPIC event we'll organize. So we organize physical meeting and online meetings. About physical meetings, so we have this EPIC members delegation in Taiwan in September. Then we'll have a meeting at European Space Agency on the photonics for new space, focus on optical communication, then something at SEDI-ATI in Austria on miniaturized optics, something on laser microprocessing at light conversion, and then in October, something on quantum technology at Quantum Effects, and on vision systems at Vision. And then in November, we have also another delegation trip to India, in the beginning of November. About online meetings, so tomorrow, we have a market and technology report on perovskite, current and future application by Bruce Bateman. And we have also something in September on membership benefit information and updates for EPIC members. And then two other OTMs, one on the photonic hybrid integrated circuits, and one in October on neuromorphic cameras. Few words also about the value chain and companies which register for today's OTM. So as I told you, we cover all the photonics value chain, all the photonic industry. So we have equipment manufacturers, end user integrators. We have also components and modules providers, metrology and testing companies, software design materials, R&D, which is quite large today for this OTM, for this topic. But you will have access to this on the webpage of the event after this event. Few words about the agenda of the today's OTM. So we'll start with Claire Guyonnet and Julien Crouzilles from SEDI-ATI. We'll talk about optical fibers for underwater applications. Then we'll continue with Casey Sapp from VideoRay. We'll talk about using virtual reality to save the oceans. We have a presentation by Emmanuel Boss from the University of Maine, and he will try to answer the question, why study the optical properties of the ocean. We have also a presentation from Andrew Durand from Pixie, who will give us an overview of what Pixie provides to the industry. Maybe yellow scan one option because Michel is not here, so we'll check this later on. We have a presentation by Fraser Daglish from BIMC. You will talk further about turbid water and extended range 3D imaging and communications. Then Glow Photonics with a presentation by Devang Naik. and we'll end this online technology meeting with a presentation by Eleanor Bosch from CSEM. And Eleanor will talk about flash lidar for bathymetry using 2D SPAD array. So thank you again very much for your participation, and do not hesitate to ask questions after each presentation. We have time for this, so feel free to raise your hand through Zoom and ask any question you will have. And yeah, let's start with now our first speaker, if they are here, but it seems that they are not here yet. And then if they are not here, I will ask you, Casey, to start first with your presentation. So I stop sharing my screen. And Casey, if you want to start and share your presentation.
All right. I am going first, everybody. Good to be here. I have got, we'll do 10 minutes, and I'm going to hide the meeting controls. Hopefully that helps a bit. And so I want to talk about multi-view and 360 cameras, and then I'm able to answer any questions. I'm going to fly through some slides. So the first thing I just want to say is that for those of you who are interested in multi-view or 360 camera technology, happy to talk more about it. And I've got a ton of experience. And my now company VideoRay is working on a number of different applications. And so that's kind of the call to action. If you have any questions or wanting to explore this, please reach out. So I had a company that was completely focused on multi-view and 360 camera technology development for about 6 years. And then it was acquired by VideoRay about 9 months ago. And so VideoRay is now scaling and deploying some of the products and capabilities we had onto their vehicles and other vehicles. I'm based in St. Pete, Florida, at a place called the Hub Maritime and Defense Technology Center. And for any of you who are in this area, would love to meet you. So about 10 years ago, I started building many of the first underwater 360 cameras, and through that built some of the most high resolution camera systems in the world, some of the first 360 live streaming, a lot of the first 360 storytelling, and then did a lot of prototyping and turned some of them into more formalized products. But it's a very bespoke and niche industry to shoot underwater 360, and so I've spanned the gamut of robotics and education and storytelling. And so through that, I've really settled in industrial applications in robotics as robots, AUVs, ROVs need better perception and better interfaces to have situational awareness for control, both through manual teleoperation and autonomy. And so I've started with these big Hollywood cameras is where I cut my teeth. And I've now moved to a very high performing, small, compact cameras, and which is what VideoRay is working on. I won't talk much about that today, but I'm just giving you kind of an overall sense of the types of systems that I built in the past that were for SeaWorld and MSG Sphere and National Geographic and BBC and Google. And through that, I built over 50 prototypes and camera systems, which have been used for various applications. And I've just had a lot of fun in terms of trying to figure out the trade-offs around resolution and image quality and size and depth and cost. And so I've through that worked with Good Morning America and billionaires and like I said, some of the natural history groups that are doing production, and had a really good time doing it and getting paid to R&D and test and experiment, which was wonderful. And so through this experience, I became quite passionate about the idea of telerobotics and taking 360 cameras, connecting them to mixed reality headsets, and using that to explore the ocean and feel like you're underwater without diving, without getting wet. And this has been tested with Monterey Bay Aquarium Research Institute and Oceanic, and now the Navy and oceaneering and more commercial companies, and it's becoming more commonplace in the deep sea to connect headsets to ROVs for manipulation and situational awareness and close quarter maneuvering. No nausea, that's all been solved. And so through pairing multi-view 3D cameras with headsets, there's just a lot of great research and academic data that's been collected and explored over the last few years that it really does benefit operators and helps even the robot itself in doing autonomy tasks to have all that additional sensing. And so through connecting cameras with headsets, we've actually found some real cool efficiencies and industrial applications to simplify tasks and decrease task completion times and improving the experience for the pilot and the operator. And have had a number of years testing this, and it's now just continuing to grow. And one of the reasons is that headsets don't work out in sunlight at the moment and have to work in somewhat constrained environments. But as they get better, you'll see this become more proliferated and more standard, I think, in the industry as people want to control more underwater robots. And so I've done a little bit of hardware, I've done a little bit of software, and through that, but ultimately it started with storytelling. It started with the concept when I put a headset on 10 years ago that having immersive experience creates empathy, which drives action and change. And there's certainly a number of different papers and research and talks that have been that are on the internet about this topic. And it's not a perfect solution by any stretch, but it certainly does give a connection to the audience that traditional 2D video doesn't, both from a storytelling perspective and in real time. And so I've worked with Meta and a number of the different groups and published 360 and immersive underwater content, and some of this is a few examples, and you can find some in the MetaQuest store and elsewhere. And I'm happy to follow up with links and share some examples. But yeah, with that, that is my little kind of 10-minute lightning talk, and I'm happy to answer any questions.
Thank you very much, Casey, for an interesting presentation and interesting activity. I was wondering, what kind of challenges do you have, in terms of integrating technologies? Can you tell us more a bit about the challenges you have today?
I mean, the biggest challenge is that underwater 360 cameras, you need the ability to synchronize. You need the ability to handle large amounts of data and do compression. If you want to do real things real time, you need to do things on the edge. You don't want to have large rendering and compute at the top side, which just increases cost and barrier to entry. And so having to figure out this, the calculus of cost and size and compute and also latency. If you're going to do things in real time, you need to have near zero latency. And IP cameras and cinematic cameras don't do that. And so the camera that I've been working on for the last 2 years, that's now just getting sold to the military and through VideoRay, is an NVIDIA-based multi-view system that can do up to 6 cameras and at different resolutions, but essentially 4 4K cameras. and then through that do real-time stitching and image enhancement and be able to uh, reconfigure the sensors in different orientations to cover the space that the operator needs to see in 2D or 3D. And so it's a very hard problem that no one's really spent a lot of time doing. You see in the automotive industry, a Tesla has cameras on every side of the car, and it's very normal for in robotics to have situational awareness and see on all sides. But underwater, this is a new concept, and it's not really being done because of size and power and weight and constraints. And so that's really what I've gone deep into the last 2 years, and now we're starting to see the benefits of that.
Mm. And regarding the constraints you have in terms of integration, are you looking for smaller cameras, higher resolution? What kind of constraint do you have also?
Yeah, I mean, so if you're in the robotics industry, if you're usually working with low bandwidth environments, and even with an ROV, you're working maybe with 100 megabit Ethernet tether, and so you can't send 4K streams up that tether, and so there needs to be a number of different steps to do compression and stitching and compiling those images into one image to send up the tether that's lower resolution, and based on what you need to see, maybe you're streaming each of those sensors at 1080 and you don't need to do 4K. It really even depends on the interface that you're streaming to. And so there's just a lot of low level customizations and settings that you need to have access to in order to have any kind of success.
Okay. Thanks. Any question for Casey? You can raise your hand through Zoom. Okay, I think that we have a question in the chat, Casey. I don't know if you can read it.
I can't.
Asking. So, can you, if I understand one, can you detect object underwater with a distance of 500 meters to 1 kilometers?
So you can't. So cameras can't see that far underwater. In turbidity, it could be 6 inches to a foot. In a best case scenario, when you're in very deep water, maybe 10 to 30 feet. And so Fraser, who's talking about his lidar technology, can see 3 to 4 times that length, which is has a lot of benefits in terms of in clarity and situational awareness in harsh environments. But cameras don't have a lot of range. They're low cost, they're mature, they are easily deployed, they're lightweight, but they're compared to sonar and lidar, they've got a lot greater limitations.
Okay, thanks. And in terms of wavelengths, today you work mainly with so visible cameras. This is the main cameras you integrate in your model.
That's right. Yeah, visible RGB cameras is where we've started, and we've now been asked to work with surface vessels and integrate IR and other more novel types of sensing technology. But in terms of underwater, we've focused first and foremost on building a system architecture for being able to scale innumerable numbers of visible cameras on a vehicle, and now we're getting into higher resolutions and sensor fusion of other types of sensing technologies like multispectral and hyperspectral.
Okay, it's something
Yes,
that
IR. That's right. IR
yeah.
does not there's a comment I just saw at the top. Yeah, IR doesn't work underwater, but it does on the surface.
Okay, interesting. Thank you, Casey. Any more question for Casey? Okay, then thank you again, Casey. Thank you very much for for showing us your
You bet.
activity.
Thank you. Thanks for the time.
Thanks. So now let's move with our next speaker. So Claire Guyonnet and Julien Crouzilles from SEDI-ATI. So you are in the room. Yes.
Yes. Hello.
All right. Yeah. Hello. Hello.
So sorry for the delay. We had some issue to connect. Sorry for.
Yeah. No problem. So I'll let you share your screen and start your presentation right now.
Si, présentation PowerPoint. Can you see it?
Yes.
Okay, great. So thank you everybody for.
Just Claire, if you can just pass in the full screen mode.
Ok. Comment je fais? Je suis en diapo. À partir du début. Je l'avais pas mis. Il me semble que je l'avais mis. Tu vois, je peux pas. Reprendre le diaporama. It seems it does not work.
I think you have to close the small window here. Reprendre le diaporama. Close this. Yeah.
It doesn't work.
Ah.
Arrête le partage. Oh, je peux même pas arrêter le partage. Qu'est-ce que c'est que ça? Bah, regarde. Ah, ça y est. Ok, I restart. Attends, je l'avais mis là, tu vois, je l'avais mis en diapo comme ça. Donc normalement. Ou alors je prends celui-là. C'est peut-être. Attends, je vais faire celui-là parce que c'est celui-là que j'ai pris avant. Non, c'est celui-ci que j'ai pris avant. Je vais faire ça. Et là, je vais faire à partir. Et là, ça va marcher. Non. It's okay?
Yes, you can start.
Okay.
Thank you.
Okay, sorry. So thank you all for joining us on the EPIC Online meeting. So I'm Claire Guyonnet, in charge of sales and marketing at SEDI-ATI, and I'm here with Julien, who is our technical sales engineer. And so briefly, we will quickly present SEDI-ATI for those that does not know each other already. So we are a French company providing some fiber optics component based on fiber and to bring light into complex and extreme environmental constraints. We are about 60 people right now, and we have made last year 8 million euro turnover with an annual growth of 10%. And we expect to reach 10 million euro in 2026. We have among this turnover about 35% dedicated to export sales, mainly in Europe, due to the fact we deal with custom design and we have to be as close as possible to our customer. We have 2,022 square meter facility here in France. So we are located in the south suburb of Paris, with 4 clean rooms and 8 people dedicated to R&D. So it's growing people since we were in 2020, at the beginning of 2023, we are more about 50 people. So it's this year 10 people more. Next one. So we address different type of application from military and aerospace, sorry, energy, research, industry, medical. From that, we address different kind of environment such as high temperature, low temperature, pressure, vacuum, radiation, and so on. I think this will be on the next slide. And for product and solution, we would we should say that we have like technology portfolio rather than product portfolio, but divided in 6 type of application. We have component, multi-mode component. We have disposable probes, the product that we will present dedicated to the topic of today. We have hermetic fit-through, bundles and array, and specific patch cords for harsh environmental constraint, and disposable probes for medical application. What we call harsh or extreme environment, it comes from high temperature to low temperature, for instance, in quantum computing, for example. We have extreme pressure, ultra high vacuum, corrosive, radiation, and it can be also vibration or mechanical shocks. So if we come, just to come back, we don't draw fiber. We use different fiber from several manufacturers, but we handle here at SEDI-ATI more than 100 reference on stock, which allow us to be very reactive on prototype and with a very wide proposal from low UV to large infrared, and also with very custom fiber such as fiber with metal coated metal coating jacket, and also sapphire or chalcogenu or whatever. So if we come back to the presentation of today, which is linked to sea exploration and oceanography, we wanted to present our fiber optics solution, which is a disposable spool dedicated to a wire guide vehicle, which can be used for sea exploration and oceanography. So next. So just to explain how it works traditionally, you have the remote operative vehicle, which is a ROVS for marine exploration, which is connected to the surface vessel by an umbilical electro-optical cable. Sorry, I just want to... Comment on peut bouger ça? Quelque part. Voilà. So this cable is deployed from a winch and is electrically powered, and we use fiber for the data transfer for the HD camera or other sensor, which requires a large network. And in this case, fiber optic technology is a good usage for that application. From this, there are some constraints due to this umbilical cable, which support the vessel, and it means that it needs to be strong enough to allow the machine to be launched into the water and recovered in the event of a problem. It's also a restriction in terms of length because it's a AV cable. And it's also very difficult to go in very narrow space where, for instance, if you want to have some information on a vessel and you need to go in very narrow space, this kind of design is not very suitable. So sorry, I went too fast. Also, this cable behaves like a leash, so means that it gives you some constraint to monitor the robots. You need to have a penetrator. You need to have a traverse winding. You need to have an electrical optical rotary joint. So it's very costly and AV solution. And so, as I told you, very unsuitable for exploring shipwrecks or sea caves. So in this case, that's where SEDI-ATI solutions becomes a very interesting solution. First of all, it's a disposable solution, which is bidirectional in terms of link, and dedicated to autonomous robot vehicle, which is AUV. In this case, you have the secure and fast deployment because the fiber is linked directly on the robot. You can go up to 10 kilometers and more on request. It's a very compact solution, low weight solution, and with custom configuration also packaging. We can also have a venting hole if you need to have something very comment on dit, to go deeper in water. So, for instance, to work like this, you have first of all the parent robot, which is going down. We took the experience of E-Framer robot, which is the Victor 6000. So you carry the mini rov with this robot, which is equipped, which is assembled with a disposable probe. And then this autonomous robot can go and explore on the ship rate with this solution of fiber. Sorry. And then, I think I forgot something. Sorry. No. So you have a real-time transmission for the data on board with high resolution for the camera and sensor. And you can allow the drone guidance in the deep water. You have also to keep in mind that this is very good for deployment of high-speed deployment and over a long distance, up to 10 kilometers, which is not the case with the umbilical cable, which is used traditionally. And it's also a solution with the fiber. When the mission is finished, you just have to cut the fiber. The fiber is silica, so is no pollution under the sea with this approach. So it's a very, very promising and growing solution in this kind of application. For this, to remote from the robot and the control station, this will need to be equipped with an optoelectronic device, and this is not part of SEDI-ATI proposal. We just remain on the passive link of this solution, but we work with drone manufacturer for this part. So what we do, we find the best solution for your underwater application. We have also some solution of fiber optics hermetic fit-through for pressure. So we can add to this solution some fiber optics fit-through solution. And we develop assembly to handle both the underwater constraint, but also your constraint. And the challenge are yours. And if you have any question on this, please feel free to ask.
Thank you, Claire, for this presentation. Thank you very much. Any question for Claire and Julien? I was wondering, Claire and Julien, if you had already a project with this technology.
Yes, we have a different kind of project. So we can have some project. We have some project for exploration, but it can also be for mean action mission, also for defense.
Okay.
This underwater, and these fiber optic spools are also applicable for terrestrial application. So for robots in terrestrial application, for instance, if you need to see if there is some explosive in some area, you can bring the robot in this space. And we have a growing business in also drones, AUV, aerial drones.
Okay. Using this cable.
Using this technology. Yes.
Okay.
So this spool is the idea is to get a spool which is comment dit, disposable and very small, very lightweight, and with very long lengths. So it gives you plenty of application with that.
So today this was mainly related to defense.
Defense or exploration. So when you need to go to explore some ship underwater.
Yeah.
go. And since you work with the fiber, which is 250 micron diameter, it's very small, so you can go in very sharp area. So you are very flexible to go in your exploration.
Yes, Devang from Photonics, please, Devang.
Hello, can you hear me?
Yes.
Perfect. Thank you so much for the really nice talk. I am from Photonics. By the way, we're also a French fiber company. We specialize in hollow core fibers. I don't know for this particular application, but our fibers tend to have be more resilient against environmental changes, temperature, pressure, and whatnot. I don't know if these sorts of things are important for your applications or not, or do you want the high sensitivity to environmental conditions?
The idea is to get much more bend insensitive fiber. So that's the most important thing. And so we work with single mode fibers, working usually it's 1310, 1550 nanometer because it's communication, video communication. And bend insensitive fiber are the most appropriate. And
is polarization maintenance important or not?
No, not at all.
Okay. Well, I hope we could talk a bit more later.
Yeah. You are welcome.
Thank you, Devang. And yeah.
Sorry, yes. At the end of the presentation, you have our contact. No, maybe you have the contact on the EPIC.
Okay.
Yeah, sure. Yes. I mean, if you need to be in contact with any speakers today, you can contact me or someone from EPIC anyway.
Yeah.
Okay.
So thank you again, Claire and Julien. Thank you very much for your presentation of SEDI-ATI.
Thank you, and sorry for being late. Sorry for that.
No problem. Thank you very much.
Bye-bye.
So now I would like to ask to Emmanuel Boss, so researcher at University of Maine, to start the presentation. So Emmanuel, you will answer the question, why study the optical properties of the ocean? So you can share your screen and start the presentation. The floor is yours. Thank you, Emmanuel. So maybe you are muted because we can't hear you.
Unmute and then I'll share again.
Okay.
This talk is the lowest technology talk from all of yours, just so you know. So it's very, very basic, and it has to do with environmental optics. So the idea of using optics to study the environment. And I hope you'll find some relationship to other things you guys are doing. So why do we use optics in general for the ocean? Why do oceanographers care about the optical properties of the ocean? It's primarily for several reasons. One is the color of the ocean is seen from space, from satellites, provide us the highest resolution data on biological processes in the ocean. We have on the order of 100 research vessels in the world. And we have an ocean that covers 70% of the planet. There's no way this is sufficient to provide us information about what happens in the ocean. And since the discovery that biology, primarily biology, but also sediment processes in land-ocean interaction affect color strongly, people have started to use that color as seen from satellite as something extremely useful. And currently, there's also approach to use polarization from space and active sensors like lidar on satellites. Another application, a very important application that optical properties are used is as proxies for materials in the ocean. Anything that interacts with light in a variety of ways can then be used to develop a sensor that senses that thing in the water. And now we have a lot of robotic platforms with optical sensors on them going up and down around the world, sensing materials we're interested to, again, in order to study the environment. It can be anything from pH and oxygen, using optodes, to things that measure directly optical properties like fluorescence and absorption, and I'll get there. And finally, we've been coming into an epoch where we use automated microscopes to study the marine environment. which provide us a huge throughput of organisms, and I'll get to that in the end. So how does ocean color work? 90% of the signal actually that you're measuring from a satellite that was reflected by the atmosphere and ocean actually come from the atmosphere, as well as from glint, which is simply the reflection at the ocean surface, and from bubbles and breaking waves. So we need one of the hardest tasks that we have to do, we as my community of oceanographer interested in ocean color, is to remove the effect of the atmosphere, and extremely accurately in order to say something about what's happening in the water. And that's a big activity I'm not going to talk about at all. So what does the signal that we see in the satellite refer to? And I have a bunch of, I don't know if you can see the camera, but if you put it on the camera, I can show you what I'm talking about. So, and many of you, of course, know it. But when I talk about absorption, I mean the fact that if I have a red light and water that are green, very little of it will propagate through, as the red will be absorbed. However, the green is going to go through. So the color you see from space is first what's not absorbed. The signal also responds to scattering. So for that, I'm adding to the same water some scattering agent, and you can see that laser because I'm now shining into scattering to the side because there's some sediment or phytoplankton that scatter light in it. And finally, from space, we can see a signal that's only from phytoplankton, which is fluorescent. So I'm using here a blue laser shine into a beaker full of chlorophyll fixed in acetone, and you can see red light emitted out of it. There was no red in the laser. It's absorbed in the blue and emitted in the red. And this is, as a colleague of mine say, the only signal we measure from space that we know come from microorganisms in the ocean, organisms that are on the order of a micron, which are phytoplankton. Okay, so then with this signal, we can see the color, which is what you have on the left, the true color. A lot of it is affected by the atmosphere. You can see clouds and other things. And then we analyze the signal coming up and we divide into what we call products. Progl might be the total particle. TSM is total suspended material in the water. We might get phytoplankton out of it, or which we quantify by chlorophyll A, and we can have information about dissolved organic. This dissolved organic is basically what you have in tea. It's material that is organically derived, and it's in dissolve. It's not in particulate form, just like your tea bag, what's coming out of your tea bag at home. So this is the approach with respect to remote sensing, and this is why NASA and many other, and ESA and other space agencies invest in this science. And then there's the use of optical quantities as proxies. So let's say we want to know quantity X, but we most often cannot measure it. This is even true for temperature. We measure temperature in the ocean by measuring resistance of a material that change resistance as function of temperature. So the same happens with optical techniques, as you know. We want to measure X, we cannot measure it directly, so we measure Y, which is a function of X, and then we invert that relationship to get the proxy. So we also, with temperature in space, we measure it as a black body radiation, not directly temperature, which is the kinetic energy of molecules. So what can we do with proxies? We can do directly things like concentration of particulate material, sediment, phytoplankton particle. We can do dissolved material, the tea-like stuff. We can even do nutrients by using UV spectroscopy, like nitrate, oxygen, pH optodes, and there's a variety of other things that we can get. And even by getting an index of refraction, we can get information about salinity, because the index of refraction of water is driven by salinity, temperature, and pressure. Temperature and pressures are easy to measure. Salinity is hard. So anything that gets us. So these sensors are put on a variety of, we deploy them from research vessels, but as I said, there's very few of them. But we have these robotics tools that are sampling the ocean. There's thousands of them. The French are really good also in putting them on organisms, as you can see the seal there or in the middle. And those are cruising around the world ocean, sending data through satellites that then feed models and provide us critical information about ocean health and distribution of materials throughout the water column and the surface. And now I'm gonna end with these automated microscope that I talked to you about. The relatively new commercial sensor that we're using, there's others. These are in relatively wide utility right now. The one on the left is from Hydro-Optics, which is a French company. It's called the Underwater Video Profiler. It illuminates a liter of water, and with a camera on top, basically gets the number of pixels associated with particles in each of these images. On the left, we have the imaging flow cytobot from Leclains in the US, which can be put on a mooring and sips 5 ml of water every 25 minutes, and then one by one run them in front of a camera that is triggered by a laser, and then an image is taken. Both are for very different size of particles. You're going to see them here. The IFCB, the imaging flow cytobot, is for particles from 5 to 200 micron, triggered with fluorescence or with scattering. You can see the imaging on the right. And typically we come back from a cruise with 1 million images just from that instrument that we put in inline, and continuously, wherever the boat goes, we collect data with. We have this type of instrument on the French boat Tara that's currently cruising around Europe, soon to arrive to Greece. The UVP is an instrument that's put typically on the CTD, which is a rosette. It's a set of instruments that are connected to a winch, and they go down through the water column, taking images. You can see the images here on the right-hand side of a variety of organisms. And typically we come back from a cruise with order 10,000, several tens of thousands of images. And of course, we cannot, on our own, take these particles and divide them into boxes. Here I give you an example. So AI is deployed, and the classifications are getting better and better. Here I'm showing you an example of IFCB data taken with Tara up. Something here is not in the right. These dots should be up. These dots should be right of the, I don't know how that moved, but anyways, 3 different places along the Brazilian coast. This is a leg of Tara from Brazil into Argentina. I was on, and you can see in 3 different places, very different distribution of phytoplankton. On the left, we have a lot of what is called diatoms, siliceous organism. They form chains. This is all from surface. The moment we go to the deeper ocean, much less particle. That's in the Brazilian current. And finally, when we come back, we see a lot of these round dinoflagellate dominating the larger of the particle. This is kind of mosaic we get every 25 minutes. And what's interesting is as we get these data in quasi-real time, every 25 minutes we get a generation of this mosaic, we can use them to tell the captain where to stop to then deploy a package of sensors, deeper, more technology that requires us to stay in one spot and sample for a whole variety of other properties. So this is extremely useful for us to study the ocean. So to summarize, optical technologies, both passive and active, provide key measurements to study the ocean and organism within them. The market for optical sensor has been expanding as people are deploying it in aquaculture and in a variety of ways by which they want to monitor ocean health. And as ocean health is becoming a subject of wider public interest, more engineers and physicists are joining in devising sensors that allow us to say more about what's in the ocean and how it behaves and what it's doing. And I'll stop there. Thank you very much.
Thank you very much, Emmanuel. So any question from the audience? Maybe first from my side, how do you usually work with industry, with companies on this kind of project?
I use most of the sensors I use are commercial. So some of them might be prototype that they just developed and they want us to use to give them feedback on how they work. We're always happy to deploy new technologies. We're interested in advancing the science and getting better and better data. So sometimes there's a property we really want to have that we don't have, and we approach a company and write a proposal with them to obtain. And there's a variety of mechanisms. I know the ones in the US. I'm sure there's one in Europe where small companies or even large companies partner with academia to develop technologies and get money to usually in several phases to develop sensors. It started with a proof of concept, and then if they like it, and SBIRs, so it's small business initiatives, are one of the main mechanisms that I've been involved with when I work with a company to develop a sensor.
Okay, thank you. Yes, Devon from Photonics. Please, Devon.
Hello, thank you so much for the really nice talk. May I ask a question? Are there any particular wavelengths of light that you think are very particularly important or very interesting for these sorts of measurements? The reason I ask is we produce fibers that have a really broad spectrum, and we're hoping on partnering with people to work on sensing technologies with our fibers. And we're wondering if there's any particular wavelengths that you think is something that there's no one in the market, there's no one in this particular area.
So the wavelength we're interested are wavelengths that interact with material in the ocean. So it's those that either excite a pigment to then fluoresce in a different one. And we're always in the visible simply because this is the band that penetrates water. We don't get near IR, we don't get much UV, except in the ocean we can get some to penetrate because of absorbing materials within the water that just limit very much the depth that you can get it to do. So it also depends on whether we're using sensors that integrate over the water column. It might be a radiometer. We're just measuring the light of the ocean as it goes through the water column. Or if it's an active sensor, and then we can have much smaller distances, and then it can be any wavelength that goes from a detector to a receiver that are a certain distance apart within water with the material that's in it. So the key here is wavelength that interact with the material, either by exciting fluorescence or by preferentially being absorbed. Hyperspectral, we now move to what we call the hyperspectral era, where we basically are scanning in many wavelengths, looking for features that are associated, for example, with pigment, particularly pigment that are specific to certain type of organism that we're after. So I know it's not exactly what you asked for, but the idea, for example, may be to look for a signature of a specific algae that is toxic for an aquaculture species, and then develop a sensor that can detect it relatively easily in the environment. That could have a significant market behind it.
Okay, thank you.
You're welcome.
Thank you, Devin. And I'm also wonder, how do you see all this constellation? Now satellite constellation they are able now to monitor the Earth and also the ocean. Do you use already these data for your activity, or how do you see this new market emerging now?
Oh, it's huge. It's huge for a variety of things. I mean, there's the footprint of satellites that are in space now has gone down, that monitor the ocean with Planet, has gone down to order 3 meters. So it's used from people that are trying to trace fishing boats that are not in the place where they're supposed to be, and they're turning off their things so they're not detected. So you can protect your fishing ground, and you can see poaching, to people that are using them to try and see jellyfish or a variety of things that currently we cannot see. So and those cover the ocean daily. You get a full day. Yeah. You cannot see them with clouds, and yes, it's used to train models or drive models in terms of distribution that have to do with ocean health by companies in France and other places. Me personally, I'm trying to develop new algorithms for them so that we have more things we can say about what's happening in the ocean. So I work directly with NASA, writing proposal to them to learn more about the ocean from the observation they're making. So there's the applications are all different. Some people use them to send their fishing fleet. They know that fish tends to go to places with high chlorophyll fronts, and that's what guides where they decide where to fish. So we all are here using it for completely different application, sometimes contradictory. But that data, what's really critical with that data, it's open. So anybody can use it to whatever application they want. And because it's open, we all also improve it, because when we find bugs in the data coming down, we report it to NASA. look, there's a problem with this or that and the other. And
so it opens also new opportunities even for you.
Absolutely. Absolutely.
Yeah.
There's private companies that are taking advantage of these data for a variety.
Okay, thank you very much, Emmanuel, for your insights.
I'm sorry I'm having to run, but I'm here with family on vacation.
Yeah, I know. So thanks a lot for your availability. Bye, Emmanuel. Thanks. And now let's welcome our next speaker, Andrew Durand from Pixie. So Andrew, you will give an overview of Pixie activity. Are you here? Yes, you can see me.
Yeah, I think I'm here. Can you guys hear me okay?
Yeah.
All
So
right.
you can start sharing your presentation. The floor is yours. Thank you.
Sure. Let's just make sure we can share that. This one. Have you guys got that? Yes, there we go. Okay.
Good.
Well, it's great to be invited here to talk at Epic and this thing, and thanks very much for inviting me, first of all. Tell you a bit about me and Pixie. So I started off working with big underwater robots, taking pictures mainly for the University of Australia many years ago now, and moved back to the UK and started a company almost as a project for a few years to make underwater photographic imaging and photogrammetry much more accessible for many applications, so it can be used for more environmental and industrial applications. There's a lot of risks with taking pictures underwater with using conventional things like divers, and if you need remotely operated vessels with you have to take the village with you, and involves a lot of people. So we're all about making it easy, removing the amount of skilled people that have to work in an environment that they don't want to, and making it easy and fast and safe. So it's a little video here, shows our vehicles being used. They're quite robust, can deploy many of them. They work on pre-programmed missions, slide down to the bottom of the sea, take some pictures, a few different ways to deploy, recover them, can use quite a good at the same time. The one-man portable, and do reconstructions of things at the bottom of the sea, take a bunch of pictures, and I think that's it for that video. But yeah, so look at some of the little samples of data that I can share that we've got. This was looking at illegal dumping in a quarry that's quite close to us here. So we take pictures of things, create scale models that you can measure, and I like these pictures because people know what a car and a tire is. And I apologize if that's your car that was stolen in the images there as well. We also do environmental survey. So this was a 150 to 200 transect for siting an oyster farm on the west coast of Scotland here. We took 6 or 8 of these surveys in a few days last year for the University of Glasgow and the estate out there. That helped them site where they could put an oyster farm. We also had the remote operations, so our vehicles could be via these buoys operated completely from our office in Edinburgh. So this is the main picture there is operating in West Australia, the very North Islands of Scotland. We've also demonstrated this a few times across the Atlantic into Canada. And the boys can have cameras. We've got wind power versions. I mean, we're working on new projects that host our vehicles and with some project partners, and allow us to operate them perpetually remotely in bigger ocean environments. Well, so what do we want to talk about in photonics? I thought we'll give an overview. I'm going to make sure I buzz through this. Light, taking pictures underwater is hard, especially if you need your own light source. So if you're deep enough, not only then does the light have to get from the target to the camera, it has to go from your light source to the object back into the camera without illuminating the items or turbidity in the water. So especially with our smaller vehicles, it's quite tricky. Speed restrictions, so we fly quite close, so really limits how fast we can move, is how much light we can get and what exposure time we can use. So at the moment we can get to about 0.5 meter a second in favorable conditions, which is quite good. It's 1800 to 2400 square meters an hour, but we'd like to do more. Air-water interface is an interesting issue, that if you want to have a flat viewport, which is the easiest to manufacture and the less susceptible to damage, you're restricted in the angle of camera view that you can have because of the refractive index. I think Casey mentioned before, but yeah, we'd really like to be able to store and raw images and the auto gain, etc., that's used for often built into cameras, and those processes don't really work very well underwater. Water absorbs red light the most, and it's visible spectra, and yeah, that disappears pretty quickly. We're always interested in integrating lower cost technologies, and one thing I'm particularly interested, if anybody has any motivation or technology that could help us, is working on panoptic or light field cameras in the use of removal of turbidity. I've done a bit of work about it in the past, and I'd like to continue that. And also anybody that's got interest in post-processing technology or techniques. A little bit of a video. This is the best thing illustrated video. This is our vehicles working at night around here. There's a lot of good developments really in through water communications. There's some commercial systems available that kind of do point to point, but there's a lot more to do, and I'd really like to find partners in that space. You're fighting things like power and distance. There's really cool opportunities, I think, for networking and active navigation. That's something we've been working on. I can't say too much about that, but something I've been working on. We'd like to hear from partners that are interested in the applications of that, and also in developing it. Obviously, we're always fighting absorption. Yeah, and I think there's also opportunities for standardization. It's happened in acoustic communications with the Janus standard, and it could be possibly part of or separate from Li-Fi standards that already exist. Always interested in off-the-shelf hardware that can be used in an unusual way, and also finding vehicles on the surface. It's quite easy to do at night, as you could see in that video, but in the daytime, if anybody can think of interesting optical techniques that we could use for locating vehicles on the surface, I'd be super happy to hear about that. And finally, sensing. I thought I'd put this up just to this is the thing we're always fighting, is the absorption spectra of water. In some ways, we're quite lucky that light does go through water. I guess otherwise our eyes wouldn't work too. But we evolved in the terrestrial domain, and we can still see things underwater to some extent. But red is and infrared doesn't work too well. But lots of cool sensors that exist on the surface, and if it's in the terrestrial domain, in air, do use the infrared spectrum. Optical flow cameras, laser ranging, time of flight cameras. It'd really be good to find ways to implement those underwater. So if anybody has some ideas about how we could do that, I'd be really interested to hear and put together a project around that. Obviously, we've mentioned that fluorometers are used underwater, and other sensing applications and sensors that work in that could work in the domain too. Always interested in scale and reduction of cost. We do things at scale. We produce vehicles, are starting to produce more vehicles in bigger numbers and reducing the cost. I mean, our vehicles cost about £20,000 for the full setup, I think, at the moment, and we're working on moving that down scale. So also great for research applications if anybody's interested. We're always interested in expanding applications and accessibility, and we work with a lot of companies doing research and development. So more than happy to hear about those opportunities. And I'd like to ask if anybody thinks there's anything I've missed in our applications, I think, as well.
Thank you, Andrew. So you are a bit blur.
I don't know why I'm. Let me see if I can give me. I don't know. I don't always look like that.
But thank you. No, thank you very much for your presentation. It's also interesting to see how many challenges you have, and yeah, that Photonics could answer some of your challenges. So any question for Andrew before mine? So I have just a few questions. Okay. So Devon, please go ahead. Devon, you have a question?
Sorry, can you hear me now?
Yeah.
Yeah, sure.
Okay. Thank you so much, Andrew. It was a really nice talk. I specialize in quantum sensors, particularly quantum magnetometers that could work at high frequencies. And I'm wondering, for a lot of the imaging applications you're talking about, a magnetic induction tomography type setup can work really well underwater, especially when we're trying to look for any sort of anything with conductivity differences with respect to water. If this is kind of something that would interest you, I would love to talk. We're trying to, we already have a project on developing underwater magnetic induction tomography techniques. So yeah.
I'm sure there are a lot of applications for that, and we can take it offline. But yeah, please send me a LinkedIn or an email. I'll happily set up a time to talk about it. That would be great. Thank you.
Okay, perfect. I already did.
All right, great. Thank you.
Thank you, Devon. I was wondering how deep can go your robot.
These vehicles now are rated to 300 meters, so that's the initial target. We have a prototype vehicle that's a bit sequel squirrel, but that's rated to 6,500 meters, so that's 90-something% of the Earth's floor.
Okay.
That should be available in the next 1 to 2 years.
Okay, I didn't see any link between your robot and the bot. How do you collect data, and also how do you transmit it to the bot?
So we collect data. It's stored locally on board. We don't have any link.
Okay.
There's stored, and then when they're on surface, either the boys transport the data over Wi-Fi, or they're brought back on a vessel, and the data is removed that way.
And what is the autonomy of your robot?
How long can it operate autonomously? I think we've had them in the water for 20 hours, maybe.
Okay.
A full working day, really. We've never run out of batteries, really. So, they were designed to, and they also have solar panels so that they can stay alive. Is the idea. So you're not, for some reason, whatever operations you do means that you can't get to the vehicle. It can kind of wait there, and you'll still be able to track it.
And do you already use some kind of, for example, lidar technologies on it? Do you already integrate?
No. We just use cameras, and we have a sonar that gives us the range to the bottom. We're working with a few different partners to do different things, but in the optical domain, we don't really have much, which is why I was interested about talking today, to find people that might be interested in some projects there. So.
Yeah, great. Okay. So if we don't have any more questions, thanks again, Andrew. Thank you very much.
No worries at all.
For your interesting inputs. And now welcome our next speaker from Yellow Scan, Michel Assenbaum. So Michel, are you here? And if yes, you can start your presentation. Share your screen and start.
Yes, thank you. I'm here. Just starting. Hello.
Hello, Michel.
So thank you very much for welcoming us into this community. We are quite new to oceanography as a company, not as people, but as a company. We used to work a lot on topography. And so I will present you the company and our new bathymetric product. I'm just trying to get it into full full page modus, sorry.
So I think that you have to click on the from beginning on the left.
Yeah, thank you. It works.
Okay.
Okay.
Wait.
So as
Yeah,
I told you,
I'm sorry, Michel, we can't see your full screen.
okay.
Maybe try to.
I have a message. The screen sharing is paused. Okay, I stop and I restart.
Yeah.
Is it better now?
Loading. Yes. Yeah, that's great. That's okay. You can start. Thank you.
Okay, thank you. So as I told you, Navigator is now our first bathymetric lidar product for UAV, and we are very proud to present it here. First, a few words about the company and its history. So actually, our mission, what we gave us at the founding little more than a decade ago, is to provide the most integrated and easy to use UAV LiDAR solution for survey and mapping. So we usually work for UAV, for IIL UAVs. Some of our equipment is also used on cars and boats, on manned planes. But the most of our customer use UAVs. And our commitment is also to listen to the user feedback and to improve our products from actual field usage feedback. As we started being ourselves surveyors, it's very important to us. So the values of the companies are ambition for excellence. We always want to aim at high goals, and for example, one of the goals of our CEO is to put some LiDAR survey to a Mars mission, so in space, so very far from ocean, to trust our people. So everyone brings value in the company. This is a employee-owned company, and we try to move things all of us, and have the best possible team spirit. So the company history, actually it was launched by two people, mostly Tristan Alois and myself. He was a specialist of LiDAR data, and myself, I was a hydrographer. But our first market was topography. So we launched our first product in 2014, incorporated in 2015, had two subsidiaries created in US and in Japan in 18 and 19. And now we are growing larger. In 2021, we bought a factory building to be able to assemble our systems. And in 2024, we launched the YellowScan Navigator. We have 70 employees on 4 continents, and the R&D is really the heart of our projects. We more than 1/5 of the people working at YellowScan work on R&D, and we invest a lot of the profit. We reinvest it to the team. So now let's go into the technique. So our products are laser scanners, basically. They are a system using one or several laser heads sending signal to objects, which can be topography or seafloor, and measuring the time of flight of the signal coming back to have the distance. At the same time, we measure the angles and the position so that we can position in 3D all the measurement points. The order of magnitude is, I would say, between 20,000 and 2 million points measured per second. So it's a very effective systems to measure topography or to measure bathymetry. Our products are fully integrated with embedded battery and easy setup, so that everyone can put that on a UAV and make some survey with it. Our motto is just press the yellow button, because we try to simplify as much as possible the process on the field in order to make it feasible also in tough conditions. The systems are compact and light, of course, because they are built to go onto UAVs. Our lightest system is 600 grams and the heaviest is about 4 kilograms. And there was a really break a few years ago when we decided to make some bathymetric product, because of course Tristan and myself, we were really fond on making something which is on the coastal area, which is much more interesting for us. We started to screen all the available sensors, but no one could reach our specifications. So we started to hire people to develop our own optical subsystems for bathymetry. And so we developed the laser source with the telescope. We developed the acquisition system, so that actually our system now is quite unique. And by the way, yes, the research project we had internally was called Alligator, in order to make bathymetry. It brought us some strange issues, because at the Japanese border we wanted to import the alligator, but they told us no, it's a protected species, you can't import it. So we changed the name into Navigator, which is more neutral and no protected species until now. So it's a system which can do both topographic and bathymetric surveys. It's using a green laser. So green is of course reflected by ground, so it's no issue. And green also penetrates quite well the water. It's kind of echo of Emmanuel Boss's presentation about how the water penetrates how light penetrates water. Actually, the green-blue light is the best compromise to have long range into water. Long range is a few meters, actually. So we have a easy mounting of the system to any drone with a GRIMC, which is a standard connector. And until now, we have about 2 Secchi depth capacity. So the Secchi depth is the depth where which characterize the turbidity. So 1 Secchi depth is the depth where an object disappears from your view when you look at it. So we can go twice as deep as that usually. So I would say typically in some turbid water, it's 1 meter to a few meter. In quite clear water, we can reach up to 20 meter. So the applications are river flood risk modeling, habitat modeling in sweet or salty water, coastal oceanography and engineering, harbor and dredging surveys if it's not too turbid, and also can help to dikes and breakwater constructions. We have also some uses for hydraulic energy structure safety, for example, the studies of dams for electric power. And so we have integrated it on several single motor and multi-rotor UAVs. Here are the system specifications. We have today a precision of about 3 centimeters. The depth, as I said, 2 seki. Actually, we choose to make some a little bit complex patterns with the laser in order to cover the area with different angles, because sometimes you have shadowing by some obstacles which would impair the possibility to see the bottom, so that with these patterns we can see the bottom through different angles while the UAV is flying forward, so that we can have very few shadows. Okay, so today our wavelength is 533 nanometers, which is quite one of the standard laser wavelengths, and also the most suitable for water. We are still, I would say, investigating some other but quite near wavelengths to see if in some type of waters, for example, more turbid, we could improve the signal by having, for example, dual wavelengths. The operating altitude above the sea is between 25 and 100 meters. The scanner field of view 44 degrees, and the pulse repetition frequency is above 20 kilohertz. So you get 20,000 raw measurements per second. Of course, after that, there is a lot of signal processing, because we have to filter out the surface echoes, which are quite strong. We have to find out what is backscatter from the water column and what is backscatter from the bottom. And so I would say the main challenge today for us is the signal processing. We are working together with universities to improve that. Here are some examples of integration. So actually, mostly on the same drone, sorry. We have integration on several drones, but basically it's always the same system, which is underneath a flying object. And here are some example of results. We started with working in Japan because our Japanese subsidiary had a very strong demand for bathymetric survey. So you can see reverse surveys with I would say the typical speed of the UAV is 5 meters per second, and so the flight could last between 10 and 20 minutes. So typically, I would say we cover half a square kilometer within one flight, and with this Japanese team, which made the surveys on the left, they fly sometimes like 10 flights a day. So it's quite a productivity tool when operated like that. So in the ocean in Japan also. We were very happy to reach for the first time 18 meters, which was at that time our record. And we had also some surveys in rivers and in coastal areas in France, working together with the French Research Institute. For now, we have built several systems, but it's still the starting phase, I would say. We have not like our topographic systems, which are used by hundreds of customers. For the bathymetric system, we have still a few selected customers with very high ability to process the data. The data is acquired full wave, which is it's a kind of lidar scanning jargon, but it means that the full return of the wave is scanned at very high frequency and recorded, so that it can be post-processed and improved on a desktop afterwards. So this is a very interesting feature because most lidars just take echoes with an automatic procedure, and with this post-processing, we can, for example, get data out of what's happening in the water column, or data about bottom in areas where the signal noise ratio is not so good. So yes, just our motto, just press the yellow button. So the yellow scan systems are quite easy to use, and we are working at the R&D level to improve this ease of use. So we are quite interested in cooperation on the post-processing of signal, but possibly also on, I would say, more theoretical level on light object interaction in the maritime environment. So that's it. If someone has a question.
Okay. Thank you, Michel. Thank you very much for this presentation of this new activity for Euroscan. Really interesting. Any question for Michel? Short one? Maybe. Yeah, okay. Antti Petinen from Photonics. Please, Antti.
Yeah. Hey, thank you,
Hello.
Michel, for a very nice presentation. Can you hear me?
Yes,
Yeah.
thank you.
Yeah, excellent. Hey, I was wondering, what kind of energies do you require when you go below the water? As you said, it's typically in few meters, and in the best case, some tens of meters. But from laser point of view, since we are a laser manufacturer, just out of interest, what do you require normally? Like, are we talking about microjoules or even further?
Yes, microjoules. We are quite. We have two class 2 laser.
Okay.
So and we try to not to go further in order to make it easy to use, because if we have a too strong laser, we have to evacuate all the area in order to be able to survey, which would be quite complicated in coastal areas. Sometimes we even survey on places like beaches or so. Of course, the UAV will not fly over the people, but we need to care for eye safety in all situations. For example, if the UAV had a problem and changed his attitude, We don't want to get someone blind, so
Yeah, fully understand.
we are really careful of working with as little energy as possible, and working on the side of the post-processing and improving the way we extract the bottom from all the signal we get back.
I see. Cool. Hey, thank you very much. Maybe I'll be in touch directly to you at some point.
Yeah,
Perhaps
you're
there could
welcome.
be some collaboration. Thank you.
Thank you, Antti, for your question. And yeah, thank you again, Michel. And if you have any question to ask to Michel or the speaker, you are pleased to to contact me or other people from EPIC, and we'll be pleased to put you in contact with the speakers. So thanks again, Michel.
Thank you very much, Rami.
Thank you very much. So now let's move to our next speaker, Fraser Dalglish from BIMC. So Fraser, you will talk about turbid water and extended range 3D imaging and communication. So Fraser, please, the floor is yours. You can start your presentation. Thank you.
Yeah, hello everyone. I hope you can hear me okay. Yeah, so I tell you a little bit about BIMC Associates, and we're really a maritime photonics and laser company, and we have a small team, and expertise is really in underwater lidar and underwater, free space optics in general, including laser communications. And we bear with me. Yeah, so I'll just give you an overview of the company, and then what we've been concentrating on developing our commercial offerings, and then some of the other things that we're interested in partnering with other people to progress. But we've been working for about 5 years on the core technology, and on several contracts where we've been developing a type of lidar for underwater that really performs better than the other architectures we've experimented with in turbid water. So it's really focused on extended range in turbid water. And we've developed, in up to sort of 20 years ago, working in universities, the team have developed and validated some radiative transfer models that, and modeling software tools that allow us to predict performance of different lidar architectures in scattering waters. And so we've developed this and miniaturized synchronous scanning active electronically steered array lidar system, and we just call it the pulse laser line scan. And we have some payloads that are available commercially. They're for small UUVs, so vehicles like the Remus 100, the Ivor 3, Ivor 4, Gavia, Bluefin 9, Groltech, and Sieber. There's other small UUV manufacturers that and we're also working on developing this lidar for micro UUV platforms. So some of the even smaller ones are approximately the size of a sonobuoy, an A-size sonobuoy, like the TDSX Barracuda, the EcoSub, Sieber have a small vehicle that size as well. And yeah, we have some other interesting developments that are not commercially available on that combine optical imaging using lidar techniques with laser communications. So let me just show you an example of some imagery. That this is a single pass where we have the 120-degree pulse laser line scan on a Remus 100. It's a wreck site off the coast of Florida. And so here we're instantaneously, our cross-track dimensions about 12 meters. So we have a long, a wide swath, wider than you would get with a camera, and we're about 6 or 7 meters off the bottom. And the top figure is intensity. The middle figure is the range map, and then this is just a commercially available unit that we have that can do this. Also, for clearer water, when you're closer, it has a camera as well and a strobe, so you can co-align and co-register the lidar 3D point clouds with color and correct the color to have a sort of true color rendition of the scene. There's another example with this is a situational awareness type payload. It's a 360-degree lidar, and we had this, and we were using it the intercoastal water in Florida, and this is just showing this. So, for example, figure E and F, where we've co-registered the side scan sonar with the lidar, and you can just sort of see the improvementness what we're getting with the lidar. But typically the lidar would work alongside acoustics, because in the very turbid waters you would be relying on the acoustic sensor by itself. This is just I'll go through some of the performance parameters of the system. So this is what the payload looks like, and it goes on to a torpedo-shaped UUV. Could go on to unmanned surface vehicle, and also like an ROV. But we have our point cloud density. We're doing about 1 million points per second, so it's very high point cloud density compared to what's currently available. And it's just a gigabit Ethernet or a USB device. This the version, it's 6 inches diameter, so 152 millimeters, and about 350 millimeters in length. And it can be co-located with a camera, and we provide like the software to view the lidar imagery after a mission, and to export it to different point cloud viewing softwares. So I'll just show you some of our longer term goals, where we're wanting to combine lidar imaging in turbid conditions with with ways of I think it's really to answer this. The challenge is that underwater optical imaging, you just look at one small patch at any one time, and we're trying to, for some missions, it's important that you could look at bigger patches. If you're looking at some events that are happening, you need a more synoptic view. So I think the video is jumping a little bit, but what we're trying to show here is, with a generic UUV platform, that there's multiples of. They probably have some acoustic connectivity, but in order to use this short range optical connectivity with low latency, there's some behaviors, autonomous behaviors and synchronization that needs to be developed. And our architecture the core technology that we're working on is future compatible for these types of applications, and developing new capabilities in robotic sensing is really our longer term goal. And we are seeking partners who want to work on these types of things with us. We have a solid core technology, and we have some very strong simulation tools to explore these types of scenarios. And I just wanted to share with you a little video that we put together of our system deployed on a blue boat from Blue Robotics. And I think the video is jumping a bit, but this is local to us in Palm Beach, and it's fairly turbid water, but we this type of imager, even with there's strong sunlight and it's turbid water, we can still get very high resolution 3D point clouds with our technology. So we're quite excited about that. Well, if there's any questions, I would like to take them.
Thank you, Fraser. Thank you very much your presentation. Any question for further? You mentioned that you are looking for some partners for your project. What kind of partners are you looking for today?
Well, we're certainly not a platform provider, and so I think we're, we platform providers. There's, in small UUVs, there's quite a few offerings now, and I think having a platform provider and having customers that have a certain application, and we have some applications in mind that where being able to visualize larger swaths of the seabed in real time and relay that information with low latency to a surface asset could be a game changer. And I think that could apply to, marine science, even commercial type oil and gas type work, and even, for military. So I think, just partners for further research and development. And, we've just focused on developing the lidar payloads for UUVs. It's our main focus as we move into production. But the R&D to fully realize the potential of this technology, I think that would be a team effort, and be partners in marine science, and engineering teams that develop platforms and autonomy algorithms and signal processing, communication protocols. So
so are you open also to work with European companies or European Research and Development Center, for example? Something that you would be open to do?
Yes, I think we certainly are. We have there's an operational capability that we're building up over in the north of Scotland.
Okay, good. Further, thank you very much again for your presentation and participation. Thanks a lot. And now welcome our next speaker. So from Glow Photonics, Devon Lake. So Devon, you can share your screen and start your presentation. And
Okay, perfect. Thank you so much. Well, I want to thank all of you for coming to my talk, and I specifically want to thank Epic for actually inviting me. And one of the main reasons is I'm not an optics person, even though I work for a fiber photonics company. I'm a quantum technologies person. But we're trying to build a next generation of quantum technologies integrated inside hollow core fibers. And one of the applications that we're hoping to really explore is underwater communication and underwater navigation. In fact, we've recently won a Quantera, which is a European-wide funding to develop this technology. And we're here trying to look for partners to actually develop this technology. So I could just dive straight in. I think the main problem is GPS. The GPS is a cornerstone of everything in our society. It's allowed so many advancements. However, the immense value of GPS to the world economy is looking more like an over-reliance on a single vulnerable aging technology, susceptible to solar activity, and more importantly, it's acceptable to jamming. With the recent war in Ukraine, we could see many instances of jamming or spoofing of GPS and GNSS signals. But most importantly, they don't work underwater. Now, we want to create another type of navigation system, which is based on a different sort of idea. Instead of using satellites and atomic clocks to be able to precisely determine your position underwater, we want to use magnetic fields. In particular, we want to use the natural magnetic fields that already exist in the Earth's atmospheric system. So this is a cartoon sort of drawing of the different parts of the Earth's atmospheric system. And there's a certain type of magnetic field which we all know about. This is a magnetic field that the traditional compass measures. This comes from a fluid and a solid core. And this is amazing in terms of what it allows us to do. However, it gives us the orientation of where we are on the Earth, but not the location. It gives us north and south. However, there's another magnetic field which is often overlooked. This is a magnetic field that comes from the lithosphere, the first tens of kilometers of the Earth right underneath us. Now, this is composed of many minerals which have been deposited via volcanic outflow. And this volcanic outflow has very specific spatial geometry, so unique that if you can measure the distribution of minerals right underneath your feet and compare it to a map, you can precisely know your position on the Earth. What's shown here, this is actually real data from the NASA probes that measure magnetic fields. These are just the magnetic fields coming from the lithosphere. And you can see the very interesting patterns which come about due to the unique configuration of minerals in the lithosphere. So if you can in principle measure these magnetic fields, you can actually know where you are on the planet without the need of any sort of satellite or atomic clock technology. Now, to give you an idea of why this hasn't been done before, is here's a little graph about the different magnetic fields that come in the Earth atmospheric system and their magnetic field strength. What's plotted on the y-axis is the magnetic field strength, and on the x-axis, what we call the spherical harmonic degree, which is a relative idea of the spatial distribution and the uniqueness of the spatial distribution of the Earth. Now, the red ellipse is what's coming from fluid core, solid core. That's what everyone knows, and it's the strongest magnetic field. You can see that all the different parts of the Earth's atmospheric condition creates a different magnetic field with a different spatial distribution. And the blue blob is a magnetic field that comes from the lithosphere. And there's a really nice range in terms of spatial distribution of magnetic fields where it does not overlap with any other source of magnetic fields. So if we can access this blue blob, we could create a system that could actually measure the spatial distribution of magnetic fields under your feet and use that for a new type of navigation system. But if you notice, these magnetic fields are weak, from a picotesla to the nanotesla. And more importantly, they're right next to the strong magnetic field of the Earth's core. It's 3 to 4 orders of magnitude larger. The most conventional magnetic field sensors just saturate at that point, even if they could measure these small fields. But more importantly, we don't want to just measure the magnetic fields. We need to measure the direction of the magnetic field to know precisely where we are. As a result, we turn to quantum technologies. Now, this is actually my lab that I built for my PhD. It's an ultra-cold atoms laboratory where we're able to take atoms, strontium, potassium, lithium, and cool them down to 1 nanokelvin temperatures. Because at these temperatures, we can create quantum states, entangled states that are very sensitive to magnetic fields. In fact, in this particular experiment, we could create magnetic field sensors with these cold atoms, which can measure sub-femtotesla, 100 attotesla magnetic fields, which is more precise than a single neuron at the center of the head, in principle. In the inlet that you see over here, you can see the blue blob and the red blob. Well, these are ultra-cold atoms of strontium and lithium that we're able to use to create these sort of magnetometers. These are amazing technologies, but they always stay in the lab. And the reason is these entangled states are very fragile and they need to be kept in large vacuum systems, as you can see over here. And these vacuum systems have, for now, been not miniaturizable. But with these systems, we're able to do amazing things. Now, I won't go over this that much unless you have really strong questions. But the most important thing is we could create a very particular type of quantum entangled state called the dark states. These dark states are extremely sensitive to magnetic fields. In this particular realization, we're able to get to 100 femtotesla or root hertz sensitivities, which is more than enough to measure the magnetic field of the Earth. However, for now, it has not been transportable. Our goal or aim with the project, with this EU project, is to compress the capabilities of these quantum optics laboratories inside a hollow core fiber and to create quantum sensors which can fit in the palm of your hand. We want to reduce the volume of these quantum sensors from meters cubed to hundreds of micrometers cubed. And we want to do that using a proprietary technology from Photonics, which is where I'm based. And these are the hollow core fibers. So I think most of you know these, but just to do a brief introduction, instead of a solid glass core in which the light propagates, we have a hollow center, as you can see on the top left. We have this sort of a microstructure cladding array around this hollow core, which serves as the main means for light propagation. However, inside this hollow core, we can create a vacuum up to 10 to the minus 10 millibars, which is exactly what we need for quantum technologies. We can hermetically seal them. We can load it with atoms and create a very quiet environment for quantum optics. You can see the sizes and the different patterns of this. Actually, for this, we've actually been awarded several sort of prizes for this technology. But now what we're able to do is we could actually take ultra cold atoms, or cold atoms, What you see is an image of atoms at cooled out to 1 microkelvin temperature. And we could load these atoms inside the hollow core fiber. And with these temperature of atoms, we could create these quantum sensors, which can arrive at, in this particular case, picotesla level of sensitivity, but in the size of your hand. Just to give you an idea, we also go in the opposite direction. Instead of having cold atoms, microkelvin inside these fibers, we can have extremely hot atoms. In these particular cases, we can also load plasmas up to 1,000 Kelvin inside these fibers itself, if this interests anyone for application. What our hope is to create a novel quantum sensing architecture, which can incorporate all cold atoms, quantum states of light, optical coatings, but also all of the elements that we need. For example, magnetic field inductions, magnetic fields, and all the electronics inside a handheld package to measure magnetic fields, not only their strength, but also their direction. Now, we want to use this for a new form of navigation system. Now, the standards for navigation systems for underwater, for submarine and underwater, is, well, in general, standard navigation is GPS. However, the GPS does not propagate underwater. It's susceptible to solar activities, and it's susceptible to jamming by adversaries. When we go to underwater, especially submarine navigation, we go into inertial navigation systems. This is actually something I've worked at before. We used to take these ultra cold atoms, nanokelvin temperatures, and we would create atom interferometers. So it's an optical interferometer, but we use the wave-like nature of atoms to be able to create the interferometer. And with these, we could create very sensitive accelerometers. The moment you go underwater and GPS fails, you can measure your acceleration. And from the acceleration, you can know where you are. However, these are very complex and expensive. They're not compact. They have large measurement drifts, and they have low update rates. And underwater, of course, there are a lot of other really interesting and very niche applications, which are really interesting. For example, acoustic positioning systems, which try to create a type of GPS underwater with acoustic systems. However, these are not quiet, they're not available globally, and they require infrastructure. We envision a system that, first of all, can give absolute accuracy, up to, for right now, we're planning on 100 meters precision, but hopefully we're hoping on better. We want something that's unjammable. This is mainly unjammable because a magnetic field signal comes from kilometers of lithosphere, the Earth underneath us. So it's almost impossible to be able to disrupt this magnetic field by an adversary. Or we want large update rates, because if we want a ship that's traveling, we want it to be able to take larger than 10 data points per second. We want something that doesn't require infrastructure that's global and it's passive. And just to give you an idea of who we are a French startup based in Limoges, France, which is mainly known for porcelain. We're mainly an R&D company focusing on deep tech. We have about 20 employees, most of them PhDs. We have our own fiber drawing towers and our own cleaning rooms. And we have really strategic partnerships with academic institutions from around the world. And we hope to kind of continue these partnerships, not only with academics, but also other companies. So if there's anyone that's interested in these magnetic sensors for underwater navigation, but also for seabed mapping, we would really like to get in contact. Anyway, thank you so much. And if you have any questions, just let me know.
Thank you very much, Devang, for this interesting project overview. Just maybe a short question for you. I was just wondering, what can the photonics community do for you today on this project, especially?
Yeah, so especially for this project, we have atoms, but to probe the atoms, we need light, and we need very particular types of light. We need portable light sources, and we need quantum light sources, although we will handle the quantum part. But we want to be able to create a fiber. Already the sensors can be very small, but the laser is not small. So we want to create sort of the entire system, lasers, fibers, and electronics, to be able to create everything in-house. And this is something we're really looking for, this kind of capabilities. Also, I'm a quantum sensing person, but also there's a lot of, at least in the talk, we have a lot of really interesting people who work on how to take the data and convert it to a map, how to do cartography. And also, one of the big things in quantum technologies is mixed sensors. So combining classical lidar with magnetic quantum magnetometers. These are things I think can, for example, magnetic fields can really go around turbulence and turbidity. So any sort of system where you need the optics, but you're worried about the turbidity, maybe a conjunction with our systems can really help in these matters. So we're looking to open these sorts of doors.
Okay, thanks, Devang. Any question?
Yeah, Devang, this is Fraser. Thanks very much for the presentation. I just had a question because I noticed that your devices are extremely sensitive. And how do you deal with the noise floor? Because the magnetic field, the noise, particularly in coastal areas when there's a lot of marine traffic and a lot of wave action, standing waves, other natural phenomena that could introduce quite raises the noise floor. I just wondered how you kind of deal with that.
Yeah, that's a good point, and this is, I think, one of the biggest problems in some of our fields. Now, we have two ways of doing that. Our particular method, this is a very particular atomic physics sort of thing, is using different transitional atoms. We can measure different directions of magnetic field. So, for example, in the transverse direction, we use a particular line, but in the other directions, we use other lines. So what we do is we reserve one line just to measure the noise, and we take the data from that line and do a feedback to cancel all this noise. So in this sort of way, we try to cancel out all the other noise. Now, we know it's noise because of the frequencies they arrive at and the directions they arrive at. So we actively cancel out all the other things based on frequencies and based on the spatial patterns of this noise itself.
That's a great answer. Thank you.
Thank you for the question, and thanks again, Devang, for your interesting presentation. Thank you. So now let's welcome our last but not least speaker of the day of this OTM. So Eleanor Bosch, Senior R&D Engineer at CSEM. And Eleanor, you will talk about flash lidar for bathymetry using 2D SPAD array. So please, the floor is yours, Eleanor.
All right, can you guys hear me okay?
Yeah, perfect.
Excellent, thank you. As Jeremy said, my name is Eleanor Bosch. I'm here with CSEM in Switzerland. I want to give a big thank you to EPIC for including us in this series of talks. And a thank you to my fellow presenters. It's been really interesting to see all of your presentations and wonderful to learn from all of you today. I have the distinct pleasure of presenting our flash lidar technology. I'll largely be focused on this prototype system that we've been developing here at CSEM over the last few years. In the meantime, we have ongoing developments to kind of augment the technology readiness level of this system. But what I have for you today is largely focused on this nice prototype. I want to advance. There we go. To give you a little bit of background about CSEM, we're a technology transfer center located in Switzerland. The majority of our employees are here in Neuchâtel, but we have locations all over the country. We kind of sit between academia and the in-house research that we do and the Swiss industry. So we're working to get technologies up to the level that they can be transferred out and used in real-life applications. We've been around for 40 years as of this year. We have over 600 employees, about just over $1 million in turnover as of last year, and a continuously growing patent portfolio, as well as growing number of startups that have spun out of CSEM and started within the walls here. So the group that contains the flash lidar imaging group has a number of other kind of industries that we cover. So this includes quite a number of industries in space, high precision mechanisms, advanced additive manufacturing, advanced control and micro vibrations. And then we have our time and frequency specialties located in the same group as well. So people working on miniature atomic clocks and stabilized lasers, frequency combs. And then there's us alongside the FMCW LiDAR group and us, the flash imaging LiDAR group. The expertise that we've developed here at CSEM is in the system design and integration of flash lidar technologies, where we target a specific application, and then we develop a lidar that's going to meet the specific requirements there. So we started with lidars for space, and hopefully you can see in the top right corner here is an image that was taken from a system that has launched into orbit. It was up there in 2018 for the Remove Debris mission. And that was targeting space debris, being able to identify it and capture it and remove it. So they had our lidar along with them. And you can see we took this really nice depth map image of a satellite while we were up there. And then down in the bottom left of that image, you can see a camera shot of that same satellite. So we develop our lidars generally to be quite compact with high spatial resolution. Using a green laser, we've been able to transfer into the bathymetry industry as well. A couple of the applications that we've been involved in are archaeological site surveys and marine and geological system surveys. One of the ongoing projects just here in the lake, basically next to the office, is the monitoring of the evolution of an erosion line that we're able to do by repeatedly scanning over the same terrain and monitoring changes that are interesting to people who want to see the evolution of the underwater terrain. It seems we have a pretty LiDAR-aware community here in the audience, so I won't spend too much time describing direct time of flight, but I'll quickly touch on the kind of distinct feature of our LiDAR, which is that it's a flash system. And what this means is that with every laser pulse, we're illuminating the entire field of view that our detector is able to see, rather than gathering a single point at a time. What we then do is collect timing data from every single pixel, which was exposed to the backscatter from the scene in front of us. And then we do that even hundreds of times in order to get a histogram of data over the time range that we were measuring. And we detect the sort of peak in that histogram to determine the depth at which your target is sitting. That histogram data is really rich with information, so it's also possible to export all of that because it might be interesting in some cases to look at multiple echoes or to look at the water column and really understand what's going on with the full range of backscatter that we're seeing in front of us. I'll just focus on the specifications described here for our prototype system. We managed to make it quite small, 20 by 20 by 20 centimeters and 6.5 kilograms. But we didn't really aim for an optimization of size, weight, and power, because this was a system where we wanted to be able to make some modifications based on the conditions that we were measuring in. So an example of that is you can see that in the field of view row there, that we have an adjustable field of view. And this actually takes a big hit on our weight and size, because without that adjustable field of view, we can make quite a bit smaller of a system. But what it allows us to do is sort of monitor how the behavior of the system and the reflections from the environment change as we modify these parameters. So we can either optimize for a given situation or test out how each of these things work, given what we're interested in measuring and the amount of time we want to spend on the water. The sensor resolution we have in this system is 128 by 128 pixels. And we do that by tiling, I'll show you an image of this in a couple of slides. We tile 2 by 2 SPAD detectors, which are each 64 by 64 pixels. Sorry, and we were able to achieve most recently about 15 centimeters of range precision when we were measuring around 5 meters in water. And that's completely raw without any spatial averaging or anything like that. So as I said, we focus on the system design. If you look down in the bottom left corner, there's an image of the focal plane array with those 2 by 2 detectors that I mentioned. So each detector is 64 by 64 pixels, as mentioned. A nice feature of these single photon avalanche detector arrays is that they're only electrically connected on two sides. And that's what enables this doubling of resolution in both directions. It's pretty unique for SPAD technology. You don't see a lot of developers taking this approach, but we were able to really take advantage of that for this system. Then we have a couple of nice features that we've integrated to improve the signal, whether it's multiple echoes. As I mentioned before, we can export the entire histogram for all of our pixels, provided you have the bandwidth to accommodate that. Or we can export simply the most prominent peak in the data. Then we have a time gating feature, which enables us to filter out unwanted backscatter signal. And then, as I mentioned, we have this adjustable field of view. So for this prototype system, we can modify what area we're looking at, which is going to have a really big impact on how quickly you can take data over a large area, or alternatively, as a trade-off, how far you can see ahead of the detector. As has been mentioned, I think a number of times by people here, is that the data throughput on our underwater systems is quite limited. So what we've done is enabled onboard processing of these time of flight histograms. Excuse me. And this we do in order to reduce the amount of data that we pipe off of the system. It means that, you know, there's less information contained. We might return just a single one of those target returns, or a couple of them, but that enables a lot more kind of throughput of information for the survey. Here's a couple of images that we took. This was actually a couple of years ago. What you're looking at in the top image is a camera capture from, I think, a GoPro of the edge of a wooden boat. It's a special wooden boat because it's from Roman times, and they found it underwater here in Neuchâtel. And they since took it out, built a model of it, and sunk it again so that it can be observed. And in our case, we were able to take a survey of it with our lidar. So you can see in the bottom image these nice depth map captures from the edge of the boat, where the edge of the boat is very clearly visible. You can see kind of that drop down from around 3.5 meters to much closer to 4 meters down next to the boat. And then you can see some of the features of the wood on top of the boat as well. Losing my voice. Here's another set of data that we took just last year. All we've really done here is stitched the point cloud together. So again, not much spatial averaging. We wanted to kind of keep all of the detailed features. But this is a ship that has been intentionally sunk in Lac Neuchâtel for the scuba diving club. We were able to take advantage of that choice in order to have a test site for our lidar as well. So you can see these depth images that we took off of the front of the ship here. As I mentioned, we're continuously improving on this technology. One of the things that we're most looking forward to is the outcome of the validation of a new sensor that's developed also by the Fondazione Bruno Kessler in Italy. This sensor has 256 by 256 pixels. So that's again doubling our resolution along both dimensions. So really a high resolution sensor and a brand new kind of technology for SPAD sensing chips. They've integrated within the layers of their transistor logic some really nice features for bathymetric applications specifically. And as I said, it's under test right now, so we're really looking forward to how it performs. That's all that I have for today. Thank you so much for your time and for staying with me through the end of this series of presentations. I look forward to welcoming your questions. And of course, I should mention that CSEM is absolutely open to opportunities for partnerships in this space. And we're so glad to have been included in this series of talks.
Thank you very much, Eleanor, for this nice presentation of CSM and this project as well. So any question, maybe one for Eleanor? Yeah, Devang, please go ahead.
Hello, Eleanor. Thank you so much for a really nice talk. I had a question for you and maybe for anyone in LiDAR. So how important is a laser line width? And importantly, how important is having miniaturized transportable frequency references for your lasers? We're in the process of creating iodine molecular clocks, which are all fibered, like really locked to sub 100 kilohertz level lines in the 532 nanometer range. And I'm wondering if this kind of precision in a laser line width is important for you.
I'm sorry, you said the precision in the laser line width?
Well, okay, sorry. So having a laser that's very precise in laser line width, so being able to lock it to a very particular particular reference itself, and creating a very stable LiDAR laser system. How important is this for your application?
I'm going to try to answer this question, and you should stop me if I've completely misunderstood it, okay? If I've understood correctly, you're talking about a line laser, so it's not a single point. Is that correct?
Oh, no, sorry. You take a laser, which has a frequency and has a certain line width itself. And you're more or less, you're measuring the reflections or whatever from that laser itself. And if the laser is very noisy in terms of frequency, compared to if it's very precise in terms of frequency, will this affect your system at all?
Can I try to use a different, did you mean maybe pulse width?
No, line width, laser line width.
I'm sorry, I might not be the right one person to answer this because I'm not sure I understand your question. Is there someone else who might want to jump in here?
Yeah, I could take that question. This is Fraser. I think so, you know, for the laser line width is definitely a consideration, but with for a direct detection type LiDAR, you will need to have a narrow interference filter or some other type of bandpass filter to make the system perform well when you're in high levels of ambient light. So as long as your line width, and obviously you have to calculate what your group velocity dispersion will be through the optical path, but the line width that comes out the laser, once you consider the broadening of that, as long as it doesn't exceed the pass band of your filter, you should be okay. But then lasers will change with temperature. They will change the center wavelength, so you also need to consider that. There are some types of LiDAR that will need a very narrow line width laser where you're trying to recover the molecular scattering by tuning the laser continuously to some sort of absorption line. So these, I don't think we're talking about that sort of system, but the line width becomes, in a stable frequency reference, become very important when you're doing that, you know, Doppler or molecular type LiDAR, Brilliant LiDAR, for example. I don't know if that's helpful.
That's very helpful. Thank you.
Okay.
Thanks so much for jumping in, Fraser, and thanks for the question. I'll also add, you gave me the chance to look it up, so thank you. And I also was able to listen to your response. So in our case, in order to achieve the wide angle field of view that we do, we actually do need to have a rather wide bandwidth optical filter. So yeah, a super narrow line width laser doesn't necessarily provide a big advantage to this system.
Okay, thank you.
Thank you.
Thank you, Devang, for a question. Any other question for Eleanor before we close the CO team? Okay, so thank you again, Eleanor, for this presentation. Thanks a lot for your participation. And yeah, thanks to all of you for your participation, thanks to the speakers and also the attendees for the question. So I think it was an interesting meeting, you know, to talk about photonics for this application. which is a niche, to be honest. But yeah, thanks a lot for your participation. So you have a poll now about this meeting. So feel free to answer it, to take time to answer it. And yeah, thank you again, and see you next time for another EPIC meeting, physical or online. Thanks a lot. Bye-bye. Thank you.
Bye-bye.
Bye,
Thank you.
thank you.
Bye-bye. Thanks.
Bye-bye.
Thank you, Fraser. That was really helpful.
Thank you. Thanks
Thank
a lot.
you.